Hello and welcome to this lecture. We're going to continue our study of sequences. In particular, two very important properties of sequences we're going to look at. Okay, so far we saw a whole bunch of examples of sequences and series, and we saw that it seems to have a lot of variety in it. How do we look at important properties? How do we classify these sequences? Right? How do we define what properties does this sequence have? Why is it useful, etc. Okay. There are two properties we'll study. One is property of being bounded. Okay, is the sequence bounded? Does it have boundaries that it won't cross, or is it going to go unbounded in either direction, like plus infinity, minus infinity type thing? Okay. The other is monotonic. What is monotonic? Doing the same thing over and over again. Okay, that's monotonic. Does the sequence behave in the same way, or does it keep changing its behavior here and there? That's the two questions we're going to study. Okay, let's get started with boundedness. Okay, definition for bounded below, bounded above, and things like that. A sequence AN is bounded above or upper bounded by some value capital M if AN, every value of the sequence, is less than or equal to that M for all N. Okay, so that is the upper bounded definition. Very simple, right? If I say capital M is an upper bound for the sequence, clearly every value of the sequence should be less than or equal to capital M. Only then it is an upper bound for the entire sequence. Otherwise, why will it be? Right? Similarly, you can also have a lower bound, which may be small m. If you claim small m is a lower bound, what does that mean? Every value of that sequence is lower bounded by m, as in every value of the sequence is greater than or equal to m. Okay. So, if you want like a picture, okay, maybe I should draw the picture here. You want a picture. If you have the stem plot of a sequence, okay, God knows what this stem plot is. A lower bound will be here and upper bound will be here, right? So, this is the upper bound, this is the lower bound. The bound is like boundary, okay. So, you have the upper boundary, lower boundary. All the values of the sequence have to be between these two bounds. It cannot go outside. Okay, so that's lower bound, upper bound. Okay, so let's see a whole bunch of examples. So here is my natural number sequence 0, 1, 2, 3. The lower bound is clearly 0. Upper bound, there is no upper bound, right? So some people will say upper bound is infinity or something, but really there is no upper bound. Okay, no, there is no upper bound. Any upper bound you possibly come up with, I can come up with a sequence which is going value in the sequence which is going to violate it. If you say 200,000, of course I can go to 200,000 plus 1. Okay. So it's going to violate it. So there's no upper bound. Okay, nice to see that. Here is another example, minus 1 power n, right? 1 minus 1, 1 minus 1, so on. The lower bound is minus 1, upper bound is 1. Okay, never goes above 1 or minus 1. Inside 1 minus 1. Okay, so that's lower bound, upper bound. Here is the 1 by n sequence, 1, 1 by 2, 1 by 3, 1 by 4, so on. The lower bound is 0. How did I get that? This is a pretty interesting lower bound, right? Why is the lower bound 0? 1 by 4, 1 by 5, 1 by 6, 1 by 7. Every value I take, however large n may be, 1 by n will never be 0. It will always be above 0. It's positive, right? Maybe very, very small, maybe 10 power minus 200. Still, it's not 0. It's a little bit above, 0. So, lower bound is 0. What about upper bound? Upper bound is 1. Okay, every value is below 1, no? 1, 1 by 2, 1 by 3, everything is below 1 also, half, 1 by 3. So, this is a sequence, 1 by n sequence, it's lower bounded by 0, upper bounded by 1. Here is another one, we didn't see this sequence before, minus 2 power n. What is this? Minus 1, minus 2, minus 4, minus 8 and so on. There is no lower bound, because however low you may go, I will go below that, right? Minus 2 power n. As n goes up, 2 power n is blowing up to 8, 16, 32, so on, and this minus, 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 minus. There's no lower bound, but the upper bound is minus 1. Notice this sequence has an upper bound of minus 1. Everything else is negative. Below, 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 below. So, minus 1 is the upper bound. Here is yet another sequence is very interesting. Minus 2 whole raised to the power n. Notice what happens here. This one does this interesting alternate. 1 minus 2 plus 4, minus 8 plus 16, minus 32 plus 64, minus 128 plus 1256. So, what will happen here is there will be no lower bound and there will be no upper bound also. This is on the positive side also there are numbers that are blowing up, on the negative side also the numbers are blowing up. There will be no lower bound, no upper bound. Okay. So, notice just with simple examples we are seeing that all kinds of cases are possible, both upper and lower bound, only lower bound, only upper bound, all these things are possible for sequences. Okay. So, let us see a few more sequences and few more of these examples. We saw some non-trivial things, right. So, if you take an arithmetic progression, a general arithmetic progression A0 plus ND, you can quite easily argue if the common difference is greater than 0, if D is positive, then the lower bound will be A0 and there will be no upper bound. Okay. On the other hand, if D is negative, then the lower bound, there will be no lower bound and the upper bound will be A0. Okay. So, it's a very easy thing to argue. Think about it. If D is positive, you are starting with an A0 and keep on adding D. Now, if D is positive, you will only go higher and higher, right. So, and you will keep on going higher, there will be no upper bound, but the lower bound will be A0. But if D is negative, you are starting at A0 and doing step by D below, there will be no lower bound, upper bound will be A0. Let us move on to the geometric progression. Here is an example of a geometric progression. An is 2 times r power n. I have not taken a more general form, reducing it to a simple case. Notice what happens here is very interesting. You could have, for instance, r being greater than 1. If r is greater than 1, clearly you see that the lower bound is 2, right? It starts with 2. Then as n increases, r is say 1.5, 2 or 3 or something, then you are multiplying by a number greater than 1, greater than 1, greater than 1. So, it will blow up, it will just increase in value, keep on increasing, there is no upper bound. Okay. So, if r is greater than 1, there is no upper bound because we are increasing the value at every n. On the other hand, if r is between 0 and 1, you see that you are decreasing the value, multiplying by something lesser than 1. So, it reduces in value, reduces in value, reduces in value. Eventually, it will reduce, but it will never go equal to 0. It will be always above 0. So, if r is between 0 and 1, the lower bound is 0 and upper bound is 2, right, because it is upper bounded by 2 n equal to 0 is the highest value. After that, you are multiplying by something that is less than 1. Okay. So, notice how these sequences, when you are going to look at bounds, there are interesting behaviors depending on how the value of D is and how the value of R is. Okay. In particular, these things are important to know for geometric progression. If R is greater than 1, it blows up, there is a lower bound, but there is no upper bound. If R is less than 1, and R is positive, of course, we are not looking at negative R. If R is less than 1, between 0 and 1, then there is both a lower bound and an upper bound. Interesting behavior. Let us just for fun of it look at the root 2 sequence. Okay. The root 2 sequence, we will plot it. Okay. So, I have plotted it. It starts at 2 and it seems to be at 1.4 something and it is never really going down. So, graphically from the graph, we can see clearly that this root 2 sequence seems to be having a lower bound of 1 and upper bound of 2. Okay. Right. This is just graphically, I am not going to analytically prove it. You can prove it. It's an exercise. It's a challenge for you. You can, if you solve it, you can post it on the forum and be proud about it. Can you analytically prove that this sequence has this property? It's lower bounded by 1, upper bounded by 2. In fact, you can prove stronger upper bounds than 1, or stronger lower bounds than 1, stronger lower bounds than 2, upper bounds than 2. But anyway, that's a simple challenge. Can you show a lower bound of 1 and an upper bound of 2 for this sequence? Okay, try it. Okay, but at least graphically we can see it's true, right? The root 2 sequence clearly is bounded. It has both a lower bound and upper bound. Let's look at more examples, right? From a boundedness point of view, let's look at our series examples, right? So, we had our natural numbers 1 plus 2 plus so on. Clearly here lower bound is 1, upper bound is none, right? There is no upper bound. It keeps on blowing up as we increase for the series. The harmonic series and its variant, this 1 by 2 square, 1 by 3 square type series, 1 by n square series, has a very, very interesting behavior. Notice what happens here. So, just to drive home the point, I have plotted Hn, the harmonic series, for very large values of n, not very large, slightly larger values of n, up to 50. So, here the 1 by n square summation also Hn2 has been plotted up to 50. So, here you see the difference is showing very clearly, right? This Hn seems to be keeping on increasing. It's not showing a tendency to flatten that much, no? I mean, it's a little bit still increasing. On the other hand, this Hn2 is flattening much more easily. Okay. So, in fact, if you plot even to 100, 200, you will see this behavior. This Hn will not increase too much, but it will never really flatten. On the other hand, this Hn2 will flatten. Okay. So, in fact, here again from the graph, just purely from the graph, Hn, the harmonic series 1 plus 1 by 2 plus so on till 1 by n, this one has a lower bound of 1 and a no upper bound. There is no upper bound for this, at least graphically. And Hn2 on the other hand, on the graph, it seems to have a lower bound of 1 and upper bound of 2. It's clearly below 2, right? I am just picking 2 here. It's a very convenient upper bound for Hn2, which is the 1 by n squared series. The 1 by n harmonic series has no upper bound. 1 by n squared series seems to have a lower bound and an upper bound. Okay, so that's the harmonic series. Let's see our alternating series examples. The alternating series, if you plot, so once again we saw a smaller plot before, here we are seeing a plot up to 50 for the alternating series. Here again you see there is a bound, right? It's between 0 and 1. So, lower bound is 0, upper bound is 1. It does not go outside of that. So, alternating has a bound, it is bounded. The Madhava-Leibniz series, pi by 4 series is also bounded. You can plot it from 0 to 50 and you can see it seems showing a tendency where, it is bounded. It's not going to go much outside of that. Its lower bound is 0, upper bound is 1. Okay. Now, once again, I just want to say all these things, except for a few things, we have not proved analytically. We have just argued it from the graph and some very simple arguments. Maybe some of these are easy, particularly showing that there is no upper bound for Hn is a little bit non-trivial. Showing these upper bounds of 2 and all is a bit non-trivial for Hn2. Even here, the alternating series, all these things are a little bit non-trivial. If you have to analytically prove it properly, mathematically, it's a little bit more work. Maybe we'll see it later on in some other context. But for us, graphically at least, it's very convincing that this is how this has to behave. Okay. So, that's the end of the boundedness property. The next property is this monotonic property. Okay, the increasing, decreasing, non-decreasing, non-increasing property. Okay. So, this is also very important for sequences. Like I said, being bounded puts your sequence within a boundary. Being monotonic is sort of like a very strong behavior for the sequence. Okay. So, together these two things can simplify your study of sequences. Okay. What is the definition? Very simple definition, right? When do you say a sequence is increasing? If an plus 1 is greater than an for all n. Very simple definition. Increasing sequence. The next value should be above the previous value. That's increasing, right? So, that's increasing. There's also a closely associated definition saying non-decreasing. Okay. So, here there is one small change. Instead of greater, we have made it greater than or equal to. Okay. See, increasing seems to demand that at every step you have to strictly increase in value. What if you are lazy and you stay the same? It's almost like increasing, but it's not increasing. It's flat also. Sometimes increases, sometimes flat. Instead of saying such complicated things, you can say that as non-decreasing. So, it doesn't decrease. It's greater than or equal to an. So, it's a correct, precise way of saying what that sequence is. So, sequence could be increasing, sequence could be non-decreasing. But usually when we talk about sequences, we will be informal and won't make so much of a careful distinction. Okay, I'll simply say increasing to sort of mean both, and if it's necessary, we'll go in and clarify that. Okay, so there's a closely associated definition, it's the opposite of this, which is decreasing. When do you say a sequence is decreasing? If the next value is less than the previous value for all n. Notice this, for all n is important. It's always decreasing. That's what makes it monotonic. It's monotonically increasing, monotonically decreasing. Right? So, that's what's important. Likewise, here this less than and less than or equal to, we do this non-increasing. Okay, decreasing, non-increasing if it's less than or equal to. Okay. So, let's go to our examples and see each of these sequences. The natural number sequence is an increasing sequence. The minus 1 power n, the alternating sequence, is none. It's not a monotonic sequence. Why is it not a monotonic sequence? It decreases from 1 to minus 1 and then increases from minus 1 to 1. It keeps on decreasing, increasing, decreasing, increasing. It's not monotonically, it's not a monotonic behavior. So, you can't say it's an increasing or decreasing sequence. This 1 by n is a decreasing sequence, keeps on decreasing. Minus 2 power n is actually a decreasing sequence. Okay, so the value keeps on decreasing. It's of course increasing to larger and larger negative values, but it's decreasing actually. Minus 2 whole power n is none again. Okay, it's neither increasing nor decreasing. So any of these alternating things is always not monotonic. Okay, so when I say none, I mean non-monotonic. There's no monotonicity here. Okay, so these were simple examples. Let's go to the slightly more complicated examples. So let's look at more complicated examples now. The arithmetic progression that we saw, an is a0 plus nd. If d is positive, it's an increasing sequence. If d is less negative, it's a decreasing sequence, right? Easy enough to see. The geometric progression that we saw, once again, if 2 times r power n, if r is greater than 1, it's an increasing sequence. If r is between 0 and 1, it's a decreasing sequence. So easy argument we made earlier also. What about the root 2 sequence? Okay, come back to the slightly more complicated example. From the graph and the initial evaluation also, maybe it's not too clear, but it turns out it's decreasing. Okay, so I'll put a question mark there. I want you to prove it. Once again, try it. It's a bit more difficult. Maybe you can't prove it entirely, but it ends up being a decreasing sequence. Okay, so it's a little bit more difficult to prove analytically, but one can show that it is a decreasing sequence. Okay, so the root 2 sequence is decreasing. Maybe on the graph you can slightly see it. It slowly decreases, keeps on decreasing. Okay, so let's go to our series examples. The natural number series is increasing clearly, right? And the harmonic series is increasing. The 1 by n squared series is increasing. All these series are increasing because I'm keeping on adding. What about alternating? The alternating series is not monotonic. Okay, so because it decreases, increases, decreases, increases. You can see it in that picture, no? It just goes down, up, down, up, down, up. So it's neither increasing. Same thing with the Madhava-Leibniz pi by 4 series. It's clearly not monotonic. No, you just do a plot, you see that it's going up and down, up and down, up. Okay. So are these properties, what are we going to do with these properties, right? So we showed that a sequence could be bounded or non-bounded. It could be lower bounded, not upper bounded. It could be upper bounded, not lower bounded. All sorts of interesting properties like that we showed. And then we also saw monotonicity. Is it monotonically increasing, monotonically decreasing, or it's neither, it's increasing, decreasing, decreasing, decreasing. How are we going to use this? We're going to use it soon enough. These are very important properties, but at least you know how to identify these properties. And this is very important. Given a sequence, you should be able to identify whether it's bounded, whether it's increasing or decreasing. Okay. So that's the end of this lecture. We'll see how to use it in the ensuing lectures. Thank you.